The first derivative test. Hello everyone. Today, we are going to discuss the first derivative test. Now, once you have gone through the process of identifying the critical points of a function, the next crucial step is to determine their nature. Essentially, figuring out what is actually happening at those specific points on the graph. It is very important to keep in mind that just because we have found a critical point, it does not automatically mean we have found a peak or a valley. Instead, think of a critical point as a candidate for a local maximum or minimum. It has the potential to be one, but it does not guarantee it. This is where the first derivative test comes into play. This test allows us to determine whether a critical point is a local maximum, a local minimum, or perhaps neither. We achieve this by analyzing the behavior of f prime of x, the first derivative, in the regions immediately surrounding that point. Over the next few slides, we will explore the logic behind this test and walk through a step-by-step procedure to apply it. Understanding the concept. Now that we have introduced the first derivative test and the idea of critical points, let's build a deeper understanding of the underlying concept. First, it is important to remember that the first derivative, f prime of x, represents the slope of the tangent to the curve at any given point x. In practical terms, this slope tells us the direction of the function. If f prime of x is greater than 0, the slope is positive, which means the function is increasing, or more simply, the graph is climbing upwards. On the other hand, if f prime of x is less than 0, the slope is negative, indicating that the function is decreasing, which you can visualize as the graph sliding downwards. By observing how this slope changes as we move from left to right across a critical point, which we will denote as C, we can deduce the exact shape of the graph at that point. This conceptual foundation is crucial, as it leads us directly into the specific working rules we will cover in the next slide to identify maximums and minimums. The working rule. Now that we understand that the first derivative tells us whether a function is increasing or decreasing, let's look at the actual working rule for the first derivative test. Suppose we have a value, which we will call c, that is a critical point of our function f of x. First, let's discuss how to identify a local maximum. If the first derivative, f prime of x, changes its sign from positive to negative as x increases through the point c, then the function f of x has a local maximum at x equals c. To understand the visual logic here, imagine you are hiking. The function climbs upward, reaches its peak at c, and then starts descending. Next, let's look at local minima. If f prime of x changes its sign from negative to positive as x increases through c, then the function f of x has a local minimum at x equals c. In terms of visual logic, this is like entering a valley. The function descends, reaches the bottom of the valley at c, and then begins to climb back up. Once you are comfortable with this logic, we can move on to the specific step-by-step procedure to apply these rules to solve actual problems. Step-by-step procedure to find extrema. Now that we understand the logic behind the first derivative test and how the slope indicates the shape of the graph, let us walk through the formal step-by-step procedure to find the local extrema of a function. Step 1 is to find the first derivative, f prime of x. This gives us the formula for the slope of the tangent line at any point on the curve. Step 2 is to locate the critical points. We do this by setting f prime of x equal to 0 or by identifying any points where the derivative is undefined. As we discussed earlier, these points are our candidates for a maximum or minimum. Step 3 involves organizing our search. We use the critical points we just found to divide the entire domain of the function into several distinct intervals. Step 4 is where we test the behavior of the function. We pick a single test value from each of these intervals and substitute it into f prime of x. This allows us to determine if the derivative is positive or negative within that specific region, telling us if the function is increasing or decreasing. Finally, in step 5, we apply the working rule from the previous slide. by observing whether the sign of f prime of x changes from positive to negative or negative to positive as we move across a critical point, we can officially classify that point as a local maximum or a local minimum. To see exactly how this process works in a practical scenario, let us move on to the next slide and apply these steps to a real-world profit optimization problem. Real-world example: optimizing profit. Now that we have covered the theoretical framework and the working rules of the first derivative test, let us apply these concepts to a practical, real-world scenario. Please look at the scenario on the slide. We are analyzing a company's profit function, denoted as p of x, which is equal to negative 2x cubed plus 9x squared minus 12x plus 10. In this context, the profit is measured in thousands of dollars, while the variable x represents the number of units produced, measured in hundreds. Our primary objective here is to determine the specific production level, x, that will maximize the company's profit. To achieve this, we will follow the step-by-step procedure we discussed in the previous slide. Starting with step 1, we must find the first derivative of the profit function. By applying the power rule to each term of p of x, we find that the derivative, p prime of x, is equal to negative 6x squared plus 18x minus 12. This derivative represents the rate of change of profit with respect to the number of units produced. Moving to step 2, we need to locate the critical points. As we learned, critical points are the candidates for our maximum or minimum. To find them, we set the first derivative equal to 0. This gives us the equation, negative 6x squared plus 18x minus 12 equals 0. To simplify this quadratic equation, we can divide every term by negative 6. This simplifies the expression to x squared minus 3x plus 2 equals 0. Next, we factor this quadratic expression. We are looking for two numbers that multiply to 2 and add up to negative 3, which allows us to rewrite the equation as the quantity x minus 1 multiplied by the quantity x minus 2 equals 0. Solving for x, we find that our critical points are x equals 1 and x equals 2. Now, remember from our earlier slides that finding these critical points does not automatically tell us which one is a maximum or a minimum. They are simply candidates. In the next slide, we will use the first derivative test to analyze the signs around these points and determine which production level actually maximizes the profit. Testing signs of p, x dollar around critical points. Now that we have identified our critical points at 1 and 2 in the previous step, we need to determine the behavior of the function around these points. To do this, we divide the number line into 3 distinct intervals, from negative infinity to 1, from 1 to 2, and from 2 to positive infinity. First, let's examine the interval from negative infinity to 1. To find the sign of the derivative in this region, we can select any test value. Let's use 0. When we substitute 0 into the derivative function, p prime of 0, we get negative 12. Since this result is negative, it indicates that the profit function is decreasing in this first interval. Next, we look at the middle interval, which lies between 1 and 2. A convenient test value here would be 1.5. Substituting 1.5 into the derivative, p prime of 1.5, gives us a positive value of 1.5. This positive result tells us that the function is increasing as it moves through this section. Finally, we test the last interval, which consists of all values greater than 2. Let's pick 3 as our test value. When we calculate p prime of 3, we get negative 12. Because this value is negative, the function is decreasing once again. Now that we have established the signs for all 3 intervals, we can move to the next slide to apply the first derivative test and conclude whether these points are local maxima or minima. Apply the first derivative test. Now that we have tested the signs of the derivative in the previous slide, let us apply the working rule to classify our critical points. First, let us look at x equals 1. We observed that the sign of p prime of x changes from negative to positive as we pass through this point. Based on the visual logic we discussed earlier, the function is moving from a descent to an ascent, which confirms that x equals 1 is a point of local minima. Next, let us examine the critical point at x equals 2. Here, the sign of p prime of x changes from positive to negative. This indicates that the function was climbing upwards and has now started to descend, meaning that x equals 2 is a point of local maxima. Finally, let us draw a conclusion for our real-world scenario. Since the objective of the company is to maximize its profit, we focus on the local maximum we just identified. Because this occurs at x equals 2, and since x is measured in hundreds of units, we can conclude that the company should produce 200 units to achieve the maximum profit. Key takeaways. Now that we have walked through the practical example of optimizing company profit, let's consolidate everything we've learned into a few key takeaways. First, remember that the core of the first derivative test is analyzing the change in sign of f prime of x as we move across a critical point. We aren't just looking at the value of the derivative, but how it behaves on either side of the point. As we saw in our example, if the sign of the derivative changes from positive to negative, it indicates that the function was climbing up and then started descending, which confirms that we have found a local maximum. On the other hand, if the sign changes from negative to positive, the function was sliding down and then began to climb, which tells us that the point is a local minimum. It is also crucial to recognize that if there is no sign change at all, meaning the slope remains positive or remains negative on both sides of the critical point, then that point is neither a local maximum nor a local minimum. Lastly, this test is an essential tool because it remains reliable even when the second derivative test is inconclusive, which occurs when f double prime of c equals 0. Now that we have the theory and the application down, let's move to the final slide to discuss some common mistakes you should avoid when performing these calculations. Common mistakes to avoid. Now that we have walked through the theory and a practical example, let's wrap up by discussing some common pitfalls. It is very important to avoid these 3 mistakes to ensure your analysis is accurate. First, be careful not to confuse the original function, f of x, with its first derivative, f prime of x when you are picking test values for your intervals. Remember that these must be plugged into f prime of x, not the original function. This is because our goal is to test the slope of the curve to see if it is increasing or decreasing, rather than finding the actual height of the graph. Secondly, do not assume that simply because the first derivative at point c equals 0, you have automatically found a maximum or minimum. As we highlighted in the first slide, a critical point is merely a candidate. To confirm its nature, you must strictly follow the working rule and check the signs of the derivative on either side of that point. Finally, let's talk about incorrect interval testing. When selecting your test values, make sure you pick numbers that lie strictly between your critical points. If you accidentally choose the critical point itself, the result will always be 0, which gives you no information about whether the slope is positive or negative in that region. Keep these points in mind, and you will be able to apply the first derivative test with confidence.